Hello everyone, you are welcome to our class today. I am Victor Odigoma Ohia. In our today's study, we are going to be looking at the sum of a geometric progression. Remember, this should be the 18th class in sequence. Alright, we have done a lot of work in sequence, starting with arithmetic progression, down to VIC examinable questions in it, to some of an arithmetic progression, to some questions in it, down to introduction to geometric progression, and to some questions in it. And then right now we are summarizing geometric progression, and we are looking at some questions. We are going to look at some other questions also as well in it. So I implore you to hang around. We are going to enjoy this class. Okay, all right, without wasting our time, right away, I was trying to explain to us a geometric progression, and we say that it is the type of sequence in which the increase or decrease in the terms is by a constant product. A constant product is exponential. So example is something like this, the simplest I can give you. Example is something like this. If you have 3 and the next term here is 9 and the next term is 27 and 81, and this continues like that, as you can see that this is exponential. Okay, when you multiply 3 by 3 you get 9. 9 times 3 will give you 27. 27 times 3 will give you 81. Okay, this is a typical geometric sequence. Here we have done a lot of examples, wide examinable examples. You can go back there to our classes and check them out. All right, so in this matter, assuming from this is the first, second, third, fourth, assuming I want to know if I add what is first, what is second, what is third, what is fourth, down to what is to the seventh term, and I want it in an instant, how am I going to do that? Okay, is there any mathematical expression that can help me to do that instead of looking for them one after the other using Tn equals to AR raised power n minus 1, that expression? Instead of looking for them one after the other, is there any mathematical expression that can help me to be able to get it at once? Let's check out and see if there is something like that. So we have already said that let this Tn, this one will be the first term A, and this one will be AR, this one will be AR squared, this one will be AR raised power 3, yeah. And then in the introduction to geometric progression, I explained this. Please, you can check that as well. So, and this will continue down to AR raised power n minus 1. Okay. Now, it then means that if I want to add these things, these terms as they are, that is representing a real mathematical figures. Okay. It then means I can say let the sum be Sn. That is, I want to use this abbreviation to represent it. That means it can become that Sn is equals to this first term plus the second term AR plus the third term AR squared plus I will continue until I get down to the last, maybe that seventh term that I want to calculate. I want to calculate the sum from the first to that seventh term. Okay, so down to that last one, AR is for n minus 1. Okay, this will be the summation of the terms. Now, assuming we say, let us multiply through by R, that's the common ratio. This equation, you can call this equation 1. Okay, let us assume that we say, let us multiply this equation 1 by R, that's the common ratio. We will have here R, then multiplying Sn. I hope that is not too serious a matter. Just times multiplying this by R equals to, this will become AR. This will become r squared. Of course, r times r will become r squared. R times r here, this will become ar raised to power 3 plus it will continue. When r multiplies here, what will remain will be ar raised to power n. That's what will remain. A raised to power n. I'm sure you know the implication of multiplying r raised to power n minus 1 by r. That this minus 1 will remove, this is 1 raised to power 1. So this will clear this. What will remain is r raised to power n. I'm sure you will get that clearly. You see, this is an integral problem. So it's just a matter of adding the powers. When you add the powers, you can be able to, get that. So we can call this equation 2. So if I say subtract 2, this equation 2 from 1. If I say that, then I have to remove this from this. That means it have to be Sn then minus Rsn. That is this minus this. Then over here, you realize that there's nothing here that can take away this. So you will have A will remain, whereas this will take away this one. This will take away this. This will take away the next here. And this removal will continue. And then, we will have something here before this. We will have this value will exist before this one. Do we get? This value will exist before you arrive here, because we multiplied, it was this that we multiplied r with to get this. So this was existing before this. So the implication is that which is here will subtract this, and this will not have anything to take away from. So we will now have minus ar raised to power n remaining. I am trusting God that you will get it clearly. I'm not too fast. I am trying to examine it, step by step. I trust God you will get it. All right. Now, if you look at what is left here, we can factorize here, and we will have Sn in bracket 1 minus r raised to power n in bracket equals to this side. We have a in bracket 1 minus, sorry, here will be just r. This is r. Okay, so we will have Sn 1 minus r here, and here we have a in bracket 1 minus r raised to power n. If you open this bracket, you come back here. Open this bracket, you come back here. I'm sure you got that. Okay, now divide both sides by this. Divide through. Divide through. Excuse me. Divide through by 1 minus r, just 1 minus r. You will get that, of course, you have Sn into 1 minus r all over 1 minus r equals to a into 1 minus r raised to power n all over 1 minus r, so that this will cancel this, and finally what you have is Sn equals to, okay, a in bracket 1 minus r raised to power n all over 1 minus r. We call this equation 3. Let's call this equation 3 because we are there. This is the mathematical expression we use to calculate the sum of a geometric sequence. And the alternative is Sn equals to a in bracket r raised to power n minus 1 all over r minus 1. Call this equation 4. This is the alternative. Now, this equation 3 is used is used when r is less than 1, like 0.5, 0.3, this and that. You can use this. Okay, equation 3 is used when r is less than 1, and equation 4 is used when r is greater than 1. When r is greater than 1, you can use this equation 4. So my brothers and my sisters, this is how we can derive the mathematical expression for calculating the sum of a geometric progression. This is a mathematical expression. In the next video, we will start applying it. We'll start looking at how we can be able to use either of these or this. The problems I'm going to solve, I'm going to just pick them from VIC past questions directly, so that you see how you can be able to, handle problems over there. Okay, so, and then if you consider sum to infinity of a geometric sequence, that is when the case when n, let me add that as well here, when n is when n tends to infinity, you realize that when you put n here tending to infinity, this will become what? 0. Okay, and 1 minus 0 is 1. Obviously, what you are going to get is Sn equals to a over 1 minus r. So this mathematical expression is used to calculate the sum to infinity of a geometric sequence. Okay, so we can add it up there as part of the knowledge we have gotten today. All right, I have done the explanations. What remains is for us to start applying what we have learned now in solving problems, which I am going to do right in the next video. Is that okay? I'm Victor Odigoma Oya. Please like what we are doing here if we are of great benefit to you. Don't be stingy with subscribing. It doesn't take time. Just click the subscription button right there. All right. It's your way of supporting us. And then share this video to your friends out there and help them to grow as well. We are here to give back to humanity. Support us in your own way if God touches your heart, and then God will bless you. Thank you.